So your GUI window is specified in the main.ui file in the libstreetmap resources. And you can modify the GUI by editing this file. And the way you can modify the GUI is to use Glade. And the command is here. Glade libstreetmap resources main.ui. So in Glade, you can rename components, you can move the components' positions, you can add new components like text boxes. And I will show you how you do it in the demo. So this is the same code from last week, where we are drawing out all of the intersections. And in this case, I will be modifying the GUI in Glade. So I'll start Glade by the same command as that we just showed you, Glade and the main.gui file. Libstreetmap resources main.ui. So the window looks like this. So you have here the list of all of the components in the main window. And by clicking on each of these, you will be looking at, here is the outer grid. Here is the main canvas. Here is the inner grid, and within the inner grid, you have all of the buttons. And the IDs here are the strings that you specify in the program, like main canvas. So the IDs are these things. And in here, you have the orientation, you have the rows and column counts. And the row and column counts are the number of rows. So 1, 2, 3, 4, 5, 7, and columns 3 in each of these. And in the packing tab, you have the left attachment. Left attachment is the coordinate counting from the left. So if you are in the main window, this is the inner grid. If you are in the inner grid, you are 1 from the left and 0 from the top. And if you click on the main canvas, it's 0 from the left and 0 from the top. So these two are side by side. And in the bottom, you have the status bar, which is 1 from the top, and having a width of 2. So it covers both the bottom of the main canvas and the inner grid. And in here, you can preview. So this is what the window will look like. And by clicking on these things, you can then add different widgets onto your screen. So the first thing to do that I will be doing is to change the title of our program, which you should also be doing. And when changing the title of the program, you will need to make sure that this check is disabled. Then I will save by clicking on save. And if you click on preview, it will be shown here, the new title. Then let me go to the actual program when I run Mapper. So just a note, if you change the main.ui, you won't be needing to recompile your program. It's just changing one file. And if you run the program, you will see that the new title is here. Okay. I'll move on to the next thing. Before I move on to the next thing, I'll do a git status, and we can see that the file is actually changed. You can see that this file is modified. Okay. Then I can then change the packing. Remember that the left attachment and the top attachment are the positions where each of these things are. So now I want to swap the main canvas and the inner grid, which is the buttons. I will then change the left attachment of inner grid to 0, and I will go to main canvas and change the left attachment to 1. And now you'll see that they swap positions. And if you preview, it will look like this. So I'll save in Glade, and I'll go run the mapper again. You'll see that the main canvas and the buttons are swapped. That's that. I'll swap them back. And now I want to add a text entry, which you will likely need for your text box, for your search bar. So I will go to the inner grid. I want to add the text box to the end of the inner grid. So I will increment the rows count to 8. And you will see that 3 little grids appeared at the bottom. And we have 3 small grids because of this. And the column count is 3. Then I want to add a text entry. So I'll go to control and add a GTK entry. Then you'll see the cursor becomes this. Then I'll go here and click on the middle one. So this will add a text bar to the middle. I don't want it to be just in the middle. I want it to have a width of 2. So it will look like this. And if we preview, it will look like this. Then I want to add a label to the text box. Like this. Then if you click on the label and the ID, and you'll see the ID and the text on it. So now both of these have an empty ID. And if you want to use it in your program, you will need to set your ID. And in this case, I'm setting the text box to be text entry. And I'll set the label to be my text label. And if you wanted to have a different name, you can say search, and it will change. Here. Then if you preview, it will look like this. And then, because you want to use it in your program, you will need to know how to use it in your program. So by doing that, go to here and read documentation. This will open the documentation for a GTK entry, which is the text box. And in the documentation, you will be able to see all of the functions associated to it. Let's go to description. So in here, you have some of the useful things that you can go to in the same page. So it's in the same page. In the description, it will say what the GTK entry is. It's a single line text entry. And it can be used for passwords. And for passwords, because you don't want to see the actual things entered, you can use this function to set the visibility. You can add, you can read through and use these useful functions. It has an ability to display progress by using set progress fraction, and it can show icons at either side. For example, if you want to use, for the search bar, you want to put a magnifying glass or something on the side of your text bar, you can use this, use icons. And yeah, a lot of useful things in the description. And if you go to the top and scroll down, you'll be able to see all of the functions, properties, signals, types, and values, and the object hierarchy. So GTK entry is in this position of the hierarchy. In the GTK entry, from object-oriented programming in C++ that you learned in 244. In GTK entry, you are able to access everything from its parent. So all of GTK widgets, G initially unowned, G object, all of the functions and its parents. And if you want to utilize some more specific functionalities in its child, then use the child objects. And everything can be found in the documentations. So the thing that we are going to use for the GTK entry text box is to get its text. GTK entry get text. And if you click on this, it will show how this function is specified. It will return a character pointer, which is a string, given the GTK entry. And from the documentation, it says it retrieves the contents of the entry widget. This is equivalent to getting entries GTK entry buffer and calling GTK entry buffer that get text on it. And it has the parameters and the returns. Pointers to the contents of the widget as a string. And it says you must not free the string. And now let's go to our code and see how we are using this. In here, everything else are the same as last time, except we have the initial setup text entry. And in the initial setup text entry, we have the pinkify button with toggle pink with text. And in this callback function, we are using the GTK entry, GTK object, creating a GTK object called text entry, which is the ID that we gave to the text box. If you don't give an ID to the text box, or if your program cannot find the ID, it will say false. I'll save this now. It will get the object from that ID and makes a GTK entry by casting it. Then getting the text using GTK entry get text. And in this case, we're just updating the message in the status bar to be the same as the things you enter in the text box. Now, let me run Mapper. So from the code, what will it do? Can anyone tell me? From what we just saw from the code. Like I just read through the code, right? What is this code doing and what will happen in the actual program? Anyone? Can anyone tell me what this code is doing? Let's read through the code again. So in the initial setup callback function, we are creating a button called Pinkify. And the spot button is registered with a callback function toggle pink with text. And in the toggle pink with text, we are toggling the Pinkify global variable, which is the same as what we just said last time. Then we are getting the object text entry, and we are getting the text from the text entry. Then we're calling update message text, and we are refreshing drawing. So what will happen in the actual program for this code? Well, I just read through the code. So what will happen? When we're running the program, you have the text box here, you have the Pinkify button here. And if you enter anything in the text box, it won't show, like nothing's happening. You can zoom in, zoom out. What does that code do? Anything from the code unclear? So we first register the Pinkify button with this function. So every time I click on the Pinkify button, it will call this function, right? Then in this function, every time I'm getting the text from the text box. And displaying the text onto the status bar. So every time when I click on the Pinkify button, it will first make the world pink, and then it will get the text in the text box and display in the status bar, like this. Right. And if I add more things onto it, it will not show. And if I click on Pinkify again, it will make it white again, and it will show whatever is in the text bar. Okay, is that clear? So what I just showed is in Glade using the packing tab to adjust the position of all of the widgets. You can use the Gtk and to get text and a callback function to get the text. And this is the same as the code that I just showed you. And other widgets, you may also need to register callback functions with anything that connects to the widget signal. And before I move on to timing and profiling, there's something else I want to show you. Because some people might want to add on overlays on the other parts of your UI. Like if you want to add some transparent overlays on the main canvas, I'll show you how to do it. So the first thing is the main canvas. I will drag it to another position so that it's out of my way. And I'll go to, where is it? Containers, GTK overlay. And I will add it to where the main canvas was. So this, by the name containers, it can contain other widgets. Now, for the GTK overlay, I will change the ID to something that I will remember, which is main canvas overlay. Then I want to move the main canvas into the main canvas overlay. So I will go in the left window, right click on main canvas, cut it, and paste it into the main canvas overlay. So now you will see that the main canvas is now under the main canvas overlay. Then, in this example, I'm only adding a switch onto the main canvas for demonstration. So I will go to Control, GTK switch. And I will click on main canvas overlay. And add widget here. So you will see that a switch appeared here. And now I can then preview. What this will look like is this. In the main canvas area, I added a switch. And now I'll save the main.ui and I'll go run mapper. You'll see that there will be a switch on top of your main canvas. And now because the main canvas is not the top level, you will not be able to pan or zoom using your cursor anymore. You can only zoom and pan with the buttons. So that's just one thing to watch out for. You may want to adjust the levels of each overlay. Yeah. Any questions on Glade? Then I guess we can have a 10-minute break and before we continue on timing and profiling. So we are going to be back by 10:56. I'll resume. So timing and profiling is how you should do to find out where time is going in your program and how to speed it up. So what you should currently know, what we are expecting you to currently know. First, to know where time will most likely be going in your program, the first thing, big O analysis to analyze your algorithms. Theoretically, an O n square function will take longer than O n log n, theoretically, for a large enough n. And the STL library provides the complexity for most of its functions that you may use. You can also guess based on your ECE244 knowledge. For example, calling the copy constructor is slower than passing by reference. If you are calling a function with value, then you are calling the copy constructor. And this is slower than passing by reference. So in most cases where you are passing a large parameter like a vector of a lot of elements, you should be passing by reference, not calling the copy constructor. Guessing based on what you think you know is bad, but people usually do it. You can also output messages in certain functions that's being called again and again. And you can use the stopwatch to time it. These are your current toolbox that we expect you to know, and now I will introduce other methods of measuring time. Because if you cannot measure it, you cannot improve it. And by improve, we mean you want to improve the portion of your program that takes the longest time. To measure performance, the first method is to manually measure it, which means you write code to measure the time. And you can measure parts of the function or measure a function. And you can look at the measured times and see which one takes longer. And this is a lot more accurate than your stopwatch. You can then sample using a debugger. You can open your program in the debugger and pause in the middle of an execution and see where you are pausing. Usually, when you are pausing at some function, then most likely that function will be taking up the most of your time. Or you can use a profiler to do everything for you. This will cause some overhead because the profiler will interrupt your program at some sampling rate. And during the interrupt, it will measure key things that it wants. And it will also take on your disk quotas. So if you have limited disk quota, then it's not a good idea to use. So make sure you clean up your disk quota before using this. And this will work well for identifying bottlenecks that you don't know where. The first method, manually measuring the performance, works by first getting the timestamp before your region of interest, then getting the timestamp after the region of interest, and you subtract them. So you will get the actual time passed. Then you can save or output the time in your desired format, like in seconds, milliseconds, nanoseconds. For example, if we are measuring the performance of act on button press, this function, you want to, before everything, get the timestamp. Then after everything, get the timestamp. Calculate the time difference and print or record. So this will be the actual code. This is using the STL chrono library, using the high resolution clock and getting the timestamp now. Then you can subtract and you can cast it into seconds using duration cast seconds. Then this is printing out the timestamp. Is that clear? Or you can save everything to a file, because looking at scrolling through the log can be difficult. You can save everything to a CSV file, which you can open in your spreadsheet app. So in this code, if defined profiling, it will save the elapsed time and it will output everything to a CSV file and separated by commas, because CSV files are separated by commas. And this you can do for every function that you're interested in by calling a profile CSV. And how it does it is that at the beginning of the function, you save the start time. Then at the end, you pass your start time and the function name into profile CSV. And the helper function will then compute the elapsed time and save everything into your CSV file. So in this case, you will need to ensure that your CSV file is open from the beginning of your program execution, and you do not close it until the end. And this code will then generate a table like this, that it has the record of all of the functions that you called and the time in seconds for each of the functions. Make sense? And for act on button press, it will output act on button press and 30 seconds, 29.98. Now I'll show that to you in code. I'll open our golden solution. So our golden solution has everything. Our golden solution has the profiling code in it. So I'll show you what the output will look like. So I'm now compiling in release mode. Okay. And I'll open Mapper in Toronto. So I'll first turn on names, turn on subways, and I'll zoom in. So that enough details are shown, and I'll click proceed and end. And if you look at the folder, it will have the funcprof.csv. I want to visualize that. So if you just open the CSV file in here, in text editor, you'll see that everything's separated by comma. But if you open the Office tool, and I will open that file, funcprof.csv, in here. You will see that it will have the function name here and the time here. So you can see that the first load map takes 5 seconds. Then draw all features takes the longest time in the first draw. So these things are the things that are called during the first draw, and this is the total time. And we can look at the second draw. Second draw is a lot faster than the first draw because the first draw needs to load in some data structures for drawing. And if we look at the draws, it takes less time until we hit the last draw because we are drawing more details of your features. And still, draw all features takes the longest time. So that's a coarse-grained way of using timed UI. So in this case, you will be able to profile a relatively accurate timing for your functions that you profile. But it will have limitations. For example, you will need to know what code to measure to profile. You'll need to know which functions you will need to add in the profiler. But how can we figure that out? How can we know which functions we should be profiling? We go to the second way of profiling, which is in the debugger, you do a manual random sampling. In the debugger, when your program is running, you randomly pause and continue. And you look at the call stack and see where you are pausing. And the most occurrence of the most subroutine that has the most occurrence is most likely your bottleneck. So you debug, pause, look at the subroutines, then continue and pause again. And if you spend more time in a routine, it is higher probability of stopping there. And if you usually stop in the same routine, then you found the problem. And you can do the manual profiling and everything else in that routine. But there may be challenges because if your redraw function is faster than how you click on the top. So in this case, we will write a loop in your redraw function to redraw many times. So in the demo that I'm going to show you, I will be doing a redraw for 30 times for every redraw. So in this case, it will be slower than when I click it because it's redrawing 30 times. And it will be much easier to pause and see where you are. And another thing to note for is your build. The most accurate time estimates in the release mode, but you will be less able to see many functions because they are inlined in the release build because it's too optimized to see the details. So we want to use the profile build, which is optimized, but it turns off the function inlining. So it will have a fairly accurate CPU time estimate, but it can stop in any function and it will output any function. Is that clear? If anything is unclear, just tell me because I'm going really fast. I'll show you the manual profiling demo. Where's my cursor? So in this case, first, I want to turn on the non-redraws. So it's the number of redraw that happens every time. In this case, in the draw function, I'm looping it by non-redraws time. I'm going to change this one to 30 as I just put that. And then in your make file, in the make file, What's the makefile doing? Yeah, makefile usually does weird things. Let me. Okay, VS Code is doing weird things and exit and open. Okay, for some reason it's doing weird things, so it doesn't allow me to. I'll do it in NetBeans then. Problem solution. Maybe. I will open the main.cpp and I will build it in profile mode. And it should be the same in the VS Code. It's just not showing up for me in the makefile. So build in profile mode. And let's hit finish. And I'll open the debugger and I'll pause. So where are we? We can look at the call stack. So we are in the load OSM database. Continue. This is most likely load map. And then in the call stack, we are in draw feature. Continue. Pause. Draw feature. Draw feature. Draw feature again. Now we are in the application run. And if I look at the window, not this window, we have everything drawn. And let's zoom in and stop. Draw feature. Continue, stop. Because the second zoom level is loaded, so it's waiting for the application run again. Zoom in again and stop. Draw feature. So we are almost always stopping in draw all features, which means that that's the thing that's taking the most time. Um, is that clear? So that is manual profiling, where we are using the debugger and we are pausing at random times. And the most time, the function that appears the most is the function that takes the most times. And then, because that's coarse sampling by manual pause and continuous, we have tools that can do automatic performance measurements. And for the tool, it's the same thing. We compile using the profile configuration, and we can run the exerciser with profile option. And using the profile option, it will output a file called perf.data. And we can then use visualization tools to visualize that data. And it's the same thing as the manual profiling. You will also need to add a loop to redraw function so that we are focusing on redraw, not the load map. So what you will most likely have is a call graph that has all of the functions as nodes, and edges are the relationships between the functions. So which function called which function. And your colors will signify the amount of time spent. Like Draw Toronto has a 74% time, but within Draw Toronto, it will have Draw Toronto takes about 74% of total time, but 58.23% of that 74% is calling draw all features inside Draw Toronto. And the other 15.5% is calling draw all segments. This is an example called graph, and I will show that to you. So I'll close NetBeans now. And just a side note, if you want to, oh, it showed up now. If you want to do everything in VS Code, you will need to set the build target to not be in the build directory. You will need to set it to the actual working directory. So it will need to be mapper. And the launch target also to the mapper in the workspace. In case you don't know. Otherwise, the program will have problems showing the actual GUI. And I think I opened the wrong code, but yeah. And to do everything on the terminal, it's just make conf equals to profile. And because I just built with profile, I don't need to do it again. And now I want to generate the perf.data file. I'll remove the previous one because it takes too much space. So to do this, before doing this, you want to make sure that you have enough space in your disk, because this will take on a lot of space. And I'm just typing the same command as this one. The exact same command. EC297 exercise 2, run tester, draw Toronto -- profile. And what I want to actually measure. So the first thing is calling load map, and then it's calling draw map. And now I want to turn on the names and subways. And I'll zoom in until it gets slow, which is this zoom. Because it wants to show all of the details. Okay. And I'll click proceed to exit the program. And it will see that it copied profiling data to perf.data. And now I want to visualize the data by this command. ECE297 profile visualize. And I'm just clicking on tab so that I don't make typos. Then it's perf.data. And if I load it, it's really, really slow, as you may notice. Still loading because it's enormous data. Okay, it's up. So you can zoom in to the things that's having the most times. So these dark blue boxes are taking less times, like 1, 2%. But this box is taking on more, which is in the libg object. And it's called by draw Toronto, draw all features. which is taking 36.58%, and draw segment is taking 8.27%. And let's go to the other one, draw feature. So as what I just said, draw feature is taking a lot of time, and the second large thing is draw line. Then if I go to the actual code, in m2.cpp, draw lines is you doing a lot of things. And that's because it froze. That's nice. It froze. Draw all features. Draw feature. In here, it's doing a line width of 2. If I change this to 0, it will be faster. So if I close this draw line is called by draw features. So remember this value, 14.5. Let me go back. I'll remove the previous perf.data because it's too large, and I'll do another make conf equals to profile. Configuration is profile and make. Then I will do the same command as before, EC297 exercise 2 run tester draw Toronto profile. And I'll turn on names, turn on sublist, and zoom in. So it's the same sequence of actions I just did. I'll zoom in until it's showing enough details, which is the next zoom level. So you'll see that it's a noticeable speed difference as the previous zooms. Still okay, and I'll proceed. Then it will say copied profiling data to perf.data. And I'll use the same visualizer as before. EC297 profile visualize perf.data. And let's open it. And just repeating again, make sure you have enough disk space before doing this, because otherwise you will have weird things like this. If you have things like this, it's usually because of limited disk space. You know, I don't have enough disk space for this thing. Oh, so if you see something like what I just showed, that's because not enough disk space, which is really likely to happen. Subways. And in that case, actually, you can either clean up your disk space or you can do a smaller simulation, like by clicking on zoom in less times or I hope that's enough. Okay, that's too large. Yeah, just try to get a shorter test. If this try doesn't work, I'll go to our backup file. Okay, it worked. We look at it. Draw feature is here, and draw line is here. Yeah. It's actually not showing a lot of difference. But yeah, drawing a line width of 0 is a lot faster than drawing a line width of 2, but it's not showing now, but so okay. So that was the call graph. So the call graph will have colors on where everything is spent. And we can also visualize it as the flame graph, like this. So it will be a similar command with an extra -t flame graph to see the flame graph from your perf.data file. And this will show width proportional to the total time spent. So you will be able to see at each call depth function call, you'll be able to see where time is spent the most in the flame graph. And this is of arbitrary order, not the sequence of events, but it will show you approximately where everything happens in time and the proportion of each function. Let's go back and I'll post this and I'll open up the flame graph. So -t flame graph. No, this will work because it worked last time. And this is huge and slow because I'm redrawing every redraw for 30 times. And this is to remove the effect of load map. So in your own profiling, you don't necessarily need to do it unless you want to really emphasize on something. Okay, this is our flame graph. See, the lowest level is draw Toronto. Then it will call some unknown things and Here is the first draw. We know this is load map. This is load map. This chunk is load map. This chunk is the first draw because the first draw usually takes more time than the others. And you'll see that draw feature is here. And it has draw line and operator, draw all features. This is draw line. And if you click on it, it will zoom into it. And you can reset zoom here. This is the first draw. This is a second draw. See that the most time is in field poly from draw features, draw features. And the above things are STL things. Reset zoom. And the last chunk is the last draw, the last zoom, where we are showing all of the details. And you can see, press zoom in, redraw, draw all features, and draw all segments. Draw feature, get feature type, draw segment. So the largest thing is draw features, and the second large thing is draw segment. Okay. Does that make sense? Everyone knows how to read the graphs, the flame graphs. Give me some feedback. Okay. In here, the colors are actually, I feel like they're there to show contrast. Because in here, you can just look at how large they are. Yeah. The larger it is, it takes more time. And if you want to zoom in, you can click on any of these and it will zoom in. Get feature type, you can reset zoom, draw feature. You can see its close feature is taking more time than draw line. And hovering over it, it will also show you how many samples and the percentage. Everything above a function is its helper functions. It's the function that this function is calling. Yeah. Any other questions? Hmm? To open this, it's this command. EC297 profile visualize -t flame graph perf.data. So it's the same file as the last thing, the last graph. You can just visualize it in both ways. And this will just open up a browser and you'll see the SVG picture in here. Yeah, and everything's in the slide. The command is also in the slide. And the width is proportional to the total time. and in arbitrary order, not in the sequence of events, but you'll see coarsely what happens in time. And if you double click, you can zoom in onto its descendants. And I think I just did a demo. And that's it for today's tutorials. I showed a lot of demo in today's tutorial, so there's likely something unclear.